Hey everybody, so in this video we're talking about building linear, quadratic, and exponential models. So in a prior video we've already discussed building linear and quadratic functions. So here we're specifically dealing with exponential functions and what those are and how we derive those. So a linear function is really just a visual representation of an arithmetic sequence. An exponential function is a visual representation of a geometric sequence. So that's why we're starting talking about exponential functions by determining what is a geometric sequence and then how do you define that. So all geometric sequences follow this format. So here we're just going to say that some output is equal to a sub 1 times r to the n minus 1. Now, this is the general form of a geometric sequence, and you probably recognize this somewhat if you've had any dealings with exponential functions, because you probably recognize this: a times b to the x. You may or may not recognize this. A is your initial value, that's a sub 1, the first term in the sequence. R is your rate of change, or your ratio. So here that's expressed as b when we're talking about an exponential function. And then n minus 1, this is specifically dealing with sequences, but in an exponential function, that's the value that I plug in. Okay, so they do go hand in hand. So we want to determine if this sequence is a geometric sequence. Well, the way I determine that is that there must be a common ratio. I must be multiplying by the same number every time. So let's see, what did I multiply 2 by to get 10? Okay, well that looks like 5. Did I multiply 10 by 5 to get the next term in the sequence? Yes, I did. Did I multiply 50 by 5 to get the next term in the sequence? And yes, I did. So here I am multiplying by 5 every time. So yes, this is a geometric sequence because a geometric sequence has a common ratio. That's what your R represents. And then they want to know what is that common ratio. So here we're just going to say that R is 5. All right, let's look at number 2, 135 to 45, okay? What did I multiply 135 by to get 45? So here, the easiest thing to do is just divide. So 135 divided by 45 gives me 3. So that means that I am multiplying right here by 1/3. Now, this should be true throughout the entire sequence. 45 times 1/3, does that give me 15? Yes, it does. 15 times 1/3, does that give me 5? Yes, it does. So, yes, this is a geometric sequence, and my common ratio here is 1/3. Okay, let's look at this one here. 6, what do I multiply 6 by to get 18? Well, I multiplied it by 3. 6 times 3 is 18. 18 times 3, is that 24? It is not, okay? So if it fails the test one time, you cannot say it is geometric. So here, no, this is not geometric because there is no common ratio. You're not multiplying by 3 to get every term in the sequence, all right? Here on our last one, 7 times what number gives me negative 14? And that is negative 2. And now 14 times negative 14 times negative 2 gives me a positive 28. 28 times negative 2 gives me negative 56. So yes, this is geometric, and my common ratio here is negative 2. Okay, so this is how you determine if a sequence is geometric. Remember, we're talking about geometric sequences now because an exponential function is plotting a geometric sequence. All right, here in this problem, they tell us for the geometric sequence described, find the first 5 terms. So the first term is 128, that's given. So here we have 128. And they want us to find the following 5 terms. They tell us the common ratio is 1/4. So we're going to take 128 and we're going to multiply this by 1/4. That's going to give us the second term in the sequence, and that is going to be 32. So here, this is going to be 32. And now to find the third term, we're going to take 32, and we're going to multiply that by 1/4, and that's going to give us 8. And then we're going to take 8, multiply that by 1/4. That's going to give us 2. And lastly, we're going to take 2 and multiply it by 1/4, and that's going to give us 1/2. And these will be the terms of my sequence. Now, this is a table. This is no different than an XY table. I would take these values and I would plot them to generate or to illustrate an exponential function. Okay, so before we start graphing exponential functions, we're going to do one more practice set with geometric sequences. So here they want us to write the rule for the nth term. Now, the reason this is a convenient tool is because this finds a specific output of any geometric function. So you'll see this particularly with exponential growth and decay, because I want to know how much is left after so many years. So you will need an exponential function so that I can plug in a number and then determine an output. So this skill is going to show up again. So first, we have to determine, is each sequence geometric? Okay, so we determine that by finding a common ratio. So here, -4 to 20, that is -5. That's the common ratio. 20 times -5 is -100. So it does appear that these are geometric. So my first term in the sequence is -4. My common ratio is -5. So my rule here, a sub n, would be the first term, -4 times -5 raised to the n minus 1. And I want to find the the eighth term here. So in order to find the eighth term, here I would say this is going to be -4 times -5 raised to the 8 minus 1. So my eighth term here is going to be -4 times -5 raised to the 7th power. And that is going to be 312,500. All right, here we have 1 to 5, 5 to 25. So my first term is 1. My common ratio here is 5. So it looks as though I'm going to have 1 times 5 raised to the n minus 1. And then they want me to find the eighth term here. So in order to find the eighth term, I'm going to have 1 times 5 raised to the 8 minus 1. So the eighth term is 5 raised to the 7th power. So 5 raised to the 7th power is 78,125. Okay, here 729 to 243. The ratio here is going to be a fraction, so the easiest thing to do is divide. So 729 divided by -243 is -3. So what I'm multiplying by is -1/3. So my first term is 729. My common ratio is -1/3. So my nth term is going to be 729 times -1/3 to the n minus 1. All right, that's the general form for your geometric sequence. If I wanted to find the eighth term here, that would be 729 times -1/3 to the 8 minus 1. So here I have 729 times -1/3. And I'm going to raise that to 8 minus 1, or the 7th power. And that will give me -1/3. And lastly, I have 8 to 12, 12 to 18. Now, right off the bat, it doesn't look like a common ratio, but we have to test. So here I'm going to say 8 divided by 12, and that's going to give me 2/3. Okay, if I took 12 and I multiplied it by 3/2. All right, so 1.5, I do get 18. So 8 times 1.5, so here 1.5, or you could say 3/2. 8 times 1.5 or 3/2 gives me 12. 12 times 1.5 or 3/2 does gives me 18. So this is geometric. So we have that the nth term should be 8 times 3/2 raised to the n minus 1. So if I wanted the 8th term, this will be 8 times 3/2 raised to the 8 minus 1. So here I have 8 times 3/2 raised to the 7th power, and that gives me 2187 all over 16. Or I could say 136.6875. Right? It really doesn't matter, but that's going to be that output. Now again, this is very convenient, this skill, because this is what we use when we do exponential growth and decay. I'm plugging in, I'm saying find the value of a car once it depreciates. If it depreciates by 7%, find the value of the car after 5 years. So I have to have an explicit rule like this one, and then I have to be able to plug in some value to generate some output. So this skill is going to show up again. All right, that's going to be all for this video. I hope that you found it helpful. If you have any questions, please leave them in the comments, and we'll see you all in the next video.